Okay, so at the end of last week, we talked about using confidence intervals to compare the means of two different groups, and we want to just say, okay, well, we observed this group and we observed this group. Okay, do these provide evidence that the respective populations have different means? Okay, that's what we covered at the end of last week, and you had to make confidence intervals, and the general premise was that if the confidence interval for the difference between means contained 0, you did not have evidence of a difference, whereas if the confidence interval for the difference between means did not contain 0, you did have evidence of a difference. Okay. Today we're going to pretty much do something very similar, except we're going to take a different approach. Okay, so the end result is pretty much the same. We're going to be comparing two group means, or the means from two populations, and we're asking the question: do we have evidence that the means of these populations are different, or is it possible that the means of these populations are the same? But I guess the form of how this will be done is through hypothesis tests. Hypothesis tests are kind of like a statistical trial, and you set up something called a hypothesis, and you have an alternative, and then and you're presented with data, okay, or evidence, and we ask if this hypothesis were actually true, what's the probability that I would observe this data? So it's like we set up two ideas. We have the null hypothesis. This is called the H sub 0 or H naught. And we have the alternative hypothesis. And we take our data. We take our data as evidence. We ask if the null hypothesis were actually true, what is the probability or the likelihood that we would observe our data? Or something more extreme. This is the premise that we or the idea. Okay. So let me give you an example. This is something else happening here. Let's see. always one of my fears is that I lift up the board and something offensive is written. Yeah. It was just, it looked like the normal distribution, but it wasn't. Okay. We have, okay, so let's, let me just make up an imaginary scenario, okay? Okay, so let's say, go on vacation and I go to Las Vegas, okay? And let's say I play, a game. Let's say I play roulette. Okay, so this is a game of complete chance, right? It's a game of complete chance. And let's say I just decide to keep betting on black. So I don't know if you guys are familiar with roulette. It's the one with the giant wheel. You spin it. Half of the spots on the wheel are red, half are black. Well, almost half are red, half are black. There's 2 green spots. Okay, and you can bet on any of these things. And so let's say I just decide to bet on the color black. Okay, so I should win a little bit of around half the time. Okay, a little bit less, about 47% of the time. Okay, right. So so I continually bet on black. Okay. So my probability of winning is, let's just say is 47%. It's a little bit different, but just for simplicity, let's just say it's 47%. Okay, so if I play 10 games, how many games would we expect that I win?
About 5.
Okay. We would expect I win 4.7 games, okay? So if I play 10 games, we expect that I win 4.7 games, okay? Let's say what actually happens is that I win 7 games. 7 out of 10 games. So the casino manager comes out. He's angry. He says, "You won 7 games out of 10. That's more than what you should be winning. I think you're cheating." Okay. What would my defense be? Huh?
You got lucky.
That I got lucky. I got lucky. I'm just gonna say no. I'm not cheating. I just got lucky. You all just want to get lucky, right? So so I won 7 out of 10 games. So the casino, you are cheating. Okay, casino claims you are cheating. I agree. And me, I say no. I just got lucky. How dare you accuse me of cheating? Okay. Now, what could and the casino says no. According to probability, you should win 4.7 games, and you won 7. Okay. So how can I say, well, no, I just got lucky? What can I? How can I show them that got lucky. Well, we could say, okay, I'm just gonna, anybody, I can say, I just got lucky, anybody who plays roulette 10 times, some of them are bound to win 7 out of 10 times, right? This is my argument. Any old person, any random person plays roulette 10 times, some are bound to win at least 7 times. Okay. And what is the probability of winning 7 games out of 10? Do we know how to figure this out? Binomial, right? I would say, okay, the probability that someone wins 7 games out of 10, 10 choose 7, 0.47 to be 7, times 0.53 to the 3. Okay? And if you're going to accuse me of cheating after I won 7 games, you surely would accuse me if I won 8 games, or 9 games, or 10 games, right? So, anybody who plays roulette 10 times, let's just figure out the probability that you might be accusing somebody of cheating. Okay, so let's also add probability of y equals 8, y equals 9, and probability of y equals 10. Okay, so then we figure this total out. Let me hop on our calculator. So when you add all of these up, you get 0.127, 0.127. Okay? So that means if even if people were playing completely fair, not cheating at all, just playing roulette, okay? If they played 10 games, about 13% of the time, people will win 7 or more games, meaning these people would become accused of cheating. So this says if people play completely fair, there's a 0.127 chance will win 7 or more games out of 10 just by random chance. Okay? Just by random chance, or what we might call luck. Is this okay? So then I say, okay, you know, you're accusing me of cheating, but if you're using this as your rule, that anybody who wins 7 out of 10 games of roulette is going to be accused of cheating, you're going to end up accusing about 13% of your customers who are just playing fair. Okay? Now, does that seem like a lot of customers to be accusing of cheating? Kind of, right? Seems the casino would be angering about, you know, 1 in 8 of their customers who are just playing fair just because they happen to get lucky, right? I'd say, no, I just got lucky. You probably, you know, you shouldn't do this, because if this was your rule for accusing people of cheating, you're going to be accusing them about 13% of the time, even if they were just playing fair. Okay? So what we say is that the probability of us observing our data or something more extreme just by random chance is 0.127. Okay, this is not a negligible amount. Okay, this is not a small amount. Okay, so we cannot rule out the possibility what we observed happened by random chance. Yes?
How do we know if something qualifies as a small amount or not?
Okay, we'll talk about that in a moment. Okay. Okay. So my argument is that, okay, all right, I see what you're saying. 7 out of 10 games, that's more than what we expect, but that happens about 13% of the time anyway. Okay, and because it happens 13% of the time anyway, we shouldn't rule out the possibility that maybe I did actually just get lucky. Okay. Does this prove that I'm innocent and that I'm not cheating? No. Okay? I could actually be cheating. But I only played 10 games, and I won 7 out of the 10 games. So it's not enough evidence to say, you know, conclusively that I'm cheating. Okay? So it doesn't prove that I'm innocent, but it's not enough evidence to say I'm cheating. Is that all right? Okay. So I tell the casino manager, go away. All right, I'm not cheating. I out statistic to you. Okay. All right. So I get cocky and I stick around and I play the casino. I play at the casino some more. Okay. Alright, so this time, I play more. Let's say I stick around and I play 100 games. And let's say I win. That's a good number. Let me just do a quick. let's say I win 63 games. 63 games out of 100. See, casino manager comes out. You're cheating. So what's my argument? Nah, I got lucky, right? He's like, you won 63 games out of 100. I said, no. I just got lucky, right? So what do we say? Okay, well, and I said, look, you accused me of cheating when I won 7 out of 10 games. I go, oh, I had 70% win ratio back then, and I showed you that I could have just been lucky, okay? Now I'm only winning 63% of the time, and you're still going to accuse me of cheating? What's wrong with you? Right? Okay. Well, he says, well, I found my friend. He also knows statistics. So you gotta try to fool him. No. Okay. Let's see what happens. All right. Well, okay. Then, so the statistics friend says, okay, smart guy. Let's see. Let's assume you weren't cheating, okay? Let's say you actually weren't cheating, okay? Let's find out the probability that you might win 63 out of 100 games. What is the chance that you would win 63 or more games just by being lucky? Or random chance. Okay. So, how can I get this number? He says, I got R on my computer and I go do this, right? 1 minus P by no. What does this number turn out to be? Okay, so this is less than 1 in 1,000. So, I can believe that you, either you're really lucky, meaning you got there's less than 1 in 1,000 chance of this happening just by random luck, or maybe you're doing something like cheating. So what would we say now? Would we agree with what the casino's accusing, or would you say, I just got like 1 in 1,000 chance? Okay, so 1 in 1,000. That's so we could either say the casino could either believe that I'm really lucky. The 1 in 1,000, or less than 1 in 1,000. That happened to, just by dumb luck, win 63 out of 100 games. Or they might say, nah, let's just say he's cheating. Give me a lifetime ban. Please never play here again. Okay. So, because this number is so small, okay? So again, what does this number represent? This is the probability of winning 63 out of 100 games or more, or basically the probability of observing my data or something more extreme if we assumed that I weren't cheating, okay? So this is the probability of observing data or something more extreme. If we assumed I was not cheating. Okay. This probability is small so we're going to so our conclusion is that it provides evidence that my assumption about me not cheating is wrong. Okay, so it provides evidence that I could be cheating. Okay. Okay. Is that all right? The reasoning behind this thing? Now, is it possible that I was actually playing fair?
Yeah.
Yeah, okay. There's about a 1 in 1,000, or this is the probability that I was actually playing fair, okay? I could actually have been playing fair, and I could have been, you know, one of the lucky 1 in 1,000 people who won 63 out of 100 games. And I was wrongfully accused of cheating. That's possible, but the casino is willing to, because the probability of that happening is so small, the casino is willing to just say, no, we're just going to cut them off, okay? And that's the, that's how our hypothesis tests are going to work, okay?
But you can't cheat on roulette, right?
Huh? I mean, it doesn't seem like I could, right? But who knows? We may be able to rig it some way to come up with a way to cheat. I don't know. They did it in Ocean's 13, so why not, right? It's in a movie. It's got to be true. So, yeah, I don't know. Don't try to cheat at a casino. It probably just won't. It might do something worse. Okay. Okay. So set up. So how? Just I guess for hypothesis test. Okay. Okay. No. Okay. So you create your hypotheses. Your null hypothesis and your alternative hypothesis. Okay. And you know this is some statement, and this is another statement. It could be, you know, in English it might be, you know, no, I'm not cheating. Okay. And then the other is I am cheating. And then we take our data and we calculate the probability of observing our data or something more extreme if we assumed this null hypothesis were true. Okay. Our data. And then we calculate. Observing our data. that probability is large, what do we do? That probability, by the way, has a name. It's called the p-value. So if our p-value is large, what do we do? Or what did we do with our casino case? We said, well, the probability of getting our data is not small, so we can't eliminate the possibility that it happened by random chance. Okay, so when the p-value is large, we say we can't eliminate the possibility that it happened by random chance. So we can't eliminate the rule out the null hypothesis. Okay, so if the p-value is large, we cannot eliminate the possibility that our data is a result of random chance. Okay. So we do not rule out or reject the null hypothesis. On the other hand, if the p-value is small, we say that we have evidence to believe our data is not a result of random chance alone. Okay? So I conclude that the null hypothesis is false and accept the alternative. All right, so let's apply it to. Well, I guess before we move on, is this okay? All right. Okay, so let's apply it to, I guess, how we're going to approach or to chapter 7, where we're dealing with two populations, and we want to know, do the populations have the same mean or not? Okay. So in chapter 7, we've observed two samples. Okay. Each from the population. different means, or not, or have the same means. Okay. So let's look at some data here. Okay, so we have two groups, two samples, group 1 and group 2, and these are we took some rats and we exposed them to, we exposed some in group 1 to a drug, and the others we didn't, and then we cut open their brains and we measured the norepinephrine concentration. It's not easy being a rat with a mad scientist around. So we exposed those two in group 1 to a drug, and then and we cut them open and we measured the norepinephrine concentration in their brain. And then group 2 we didn't expose to the drug, and then we cut them open and we measured the norepinephrine concentration. Okay, and then so there's 6 measurements in group 1. Okay, the individual measurements themselves don't really matter. Okay, there's 6 of them. So I've got 6 here. The mean of these 6 values is 540.8, and the standard deviation of these 6 values 66.1. Okay, and over in group 2, I have 5 values. Okay, and the mean of these 5 values is 444.2, and the standard deviation of these 5 values is 69.6. Okay, so it's just nice that the book gives us these things, but you could all find these numbers yourself, right? If you had 5 numbers, you know how to find the mean of 5 numbers, and you know how to find the standard deviation of 5 numbers. So the question is, all right, so this group has a mean of 444.2, and this group has a mean of 540.8. Is this evidence that the two groups have, that their respective populations, okay? So again, group 1, these are the rats exposed to the drug toluene, and these were the control rats, so no drug. So what are the respective populations of each of these?
You mean total?
Yeah.
11.
For each one, right? So the group 1, the respective, so that we observed six mice or 6 rats, and the respective population is potentially all possible rats that are exposed to the drug. Okay? And for group 2, the control rats, their respective population is all possible rats that are not exposed to the drug. Okay? And so we want to know, is this population, the population of all rats that could be exposed to the drug, or that are exposed to the drug, does that have a different mean value of norepinephrine concentration than this population, which is all the rats that weren't exposed to the drug? Okay, so do these two things, do they have the same mean, or are their means different? That's what we're asking. Now, when we took a sample, this gave us a mean of 540, and this gave us a mean of 444. Okay? Is this evidence that the respective populations have different means? Okay? So we observed a difference question we're trying to answer. What do you guys think? Just what's your gut feeling? Yes, no, maybe?
Yeah.
Yeah,
Yeah?
sure.
Okay. So let me just throw in some doubts into your mind, and we can say, okay, well, we did see a difference of 100, or close to 100, so that seems pretty big. But look at the standard deviations. The standard deviations themselves are pretty big, and this is based only on six or 5 rats. It's tough to say. I can't look at this and say yes or no. The difference is close to 100, so it seems like it's a big difference, but I don't know. Okay, well, let's see. Okay, so what do you think our null hypothesis and our alternative hypothesis would be? So I'll put this up symbolically. Okay? The null hypothesis is that mu1 is equal to mu2, or alternatively mu1 minus mu2 equals 0. Okay, so this is either saying the means of the two populations are the same, or that the difference between the means is 0. Okay, it's basically saying the exact same thing. Alright? I guess implicitly, or what this implies, okay, so in English is that this says the difference between the means of the populations, difference between the means of the populations is 0. Okay? And what that implies is that any difference that we observe between the sample means is simply a result of the random selection process. Okay, simply the result of random selection. Meaning, just by random chance, I happened to pick 6 mice where the mean was 540, and by random chance, I happened to pick 5 mice where the mean was 444. That gave me a resulting difference of 90 whatever, okay, of almost 100. That's what the null says, okay? And the alternative states that mu1 doesn't equal mu2, or equivalently, that the difference between these two things is not 0. And this basically says the difference is not 0. And what that implies is that the difference that we observe in our samples, difference that we observe between our samples, is not just a result of random chance. Okay, because there's always going to be an element of randomness. Okay, so the difference we observe is not just a result of random selection, but also a consequence of the two populations having different means. Alright, is this okay? So, I have my null and alternative hypothesis set up, okay? So, when you do a hypothesis test, this is what's implied whenever you write the statement. This is all you end up writing on your piece of paper. You just write mu1 minus mu2 equals 0 versus mu1 minus mu2 doesn't equal 0. Or, you know, mu1 equals mu2 or something like that, okay? But when you write these statements, this is what it's implying. It's implying, this one states that whatever we observe could be, you know, chalked up to just random chance. And this one says, you know, random chance, sure, that plays an element, but it's not enough to explain everything. And something else is also happening. Okay, so what's the next step in the hypothesis? We got to calculate the probability of what? Probability of observing our data, or something more extreme, if we assume the null hypothesis were true. Okay, so that's what we're going to try to figure out. Okay, so if the null hypothesis were true, whenever I take two samples, what should the difference between the sample means be? 0, right? If the populations have the same mean, anytime I take two samples, the means of the samples should be about the same, okay? I should have a difference of about 0, but I didn't get a difference of 0, okay? So if the null hypothesis were true, okay, the distribution of y1 bar minus y2 bar should be centered at 0. Okay. What I observed is I observed a difference of what? What is that? 96, 95 96.6. So you can imagine I'm drawing up a distribution. This is the sampling distribution of y1 bar minus y2 bar, okay? So anytime I take two samples and I record the difference between the sample means, I'm expecting a difference of 0. What I observed was a difference of 96.6. Is this a large value or a small value?
Large.
Well, it all depends on what? The
Standard
standard deviation, or the standard error of this distribution. Okay, so we got to figure out our standard error. Okay, so our standard error, this should look familiar. Okay, it's standard error for a difference. Okay, so it's same as when we were dealing with confidence intervals and we had a standard error. Same type of thing. We got a standard error for a difference here. Okay, so plugging in the numbers that I have, 66.1 squared over 6 plus 69.6 squared over 5. And this gives me a standard error of 41.195. now I'm going to get something like a z-score, but it's not a z-score because what kind of distribution is this? It's almost normal. It's going to be the t-distribution, okay? And it's the t-distribution because sigma is not known. We're using our best guess for sigma by using s, okay? And so anytime we do that, we've got to compensate for the extra layer of uncertainty. So we're going to use the t-distribution, okay? Pretty much we're just going to use the t-distribution for a bunch of stuff here on out, okay? So I'm going to get basically like a z-score, but for the t-distribution, so a t-score, or what we just call a test statistic, and set up just like the like a z-score. We put in what we observed minus our mean, or what we are expecting, divided by the standard error, okay? So what did I observe? I observed a difference of 96.6. And if the null hypothesis were true, what kind of difference do I expect? I expect a difference of 0, and my standard error is 41.195. So this gives me a test statistic of 2.34. So what I observed is 2.34 standard errors away from the mean, okay, or away from 0, which is what we would expect if the respective populations had the same mean. So if the null hypothesis were true, we expect a difference of 0. What I observed was a difference of 96.6. That turns out to be a little over 2.3 standard errors from the mean. All right, so is that big? Okay. It's on the bigger side. It's on the bigger side. Okay. So
When you're saying, question.
Yeah.
When you're saying 2.34, I'm sorry.
Standard deviation.
Yeah.
Is that
or standard errors from the?
Is that like z? That would be like z 2.34.
It's not quite z. Okay, it's t. T is equal to 2.34, but same idea. It's the same idea. Okay. A z-score is how many standard deviations you are from the mean. Here we're dealing with the t distribution, and it's 2.34. How many standard errors we are away from the mean. Okay. It's a similar concept. Yeah.
And is it roughly distributed in the same way as the normal distribution? So
It's
that
roughly distributed like a normal distribution, and we actually have the table that tells us exactly how it's distributed. Okay. Now every time we use the t distribution, we've got to know what? Degrees of freedom. Degrees of freedom. Okay. So you got to figure out the degrees of freedom. And again, finding the degrees of freedom is a pain in the butt. So we're not going to do the true degrees of freedom. We're going to approximate it. And so what's our approximation in this case? None, right? We do n1 plus n2 minus 2. Okay, so we have approximately 9 degrees of freedom. Okay, other textbooks, they might say, just take the smaller one and subtract 1. And so other textbooks might say, use 4 degrees of freedom. The truth is, it's probably going to be somewhere between 4 and 9 degrees of freedom. Okay, so we have 9 degrees of freedom. And this is how the t table works, okay? Just going to barely get through, okay? The way the t table works, it's different from the normal table, is that, let's say we look at 9 degrees of freedom. Let's go to that row, 9 degrees of freedom. And it says, the t distribution is always centered at 0. It says, you see that first number, 0.883 in your t table, okay? It says if I draw a line at 0.883 and I shade everything to the right, the amount that's going to be shaded to the right, if we look at the top of the distribution, is 0.20. Okay? And then if I have a t distribution with 9 degrees of freedom, and if I draw a line at the next number, 1.383, and I shade everything to the right, the amount that's shaded there is what? 10%, 0.10. Okay? So then let me ask you this. If I draw a line at 1.0, right there, and I shade everything to the right, how much is to the right of the line 1.0?
1.5.
The answer is we don't know. We don't know the exact value, okay? But we do know, whatever it is, it's going to be more than 10%, but less than 20%, okay? So that's how we're going to use the t-table most often, okay? Because rarely, okay, I mean, if you do your test statistic and you happen to get 0.883 exactly, then you know that the amount to the right is 20%. And if you happen to get 1.383 exactly, then you know the amount to the right is 10%. But rarely is that going to happen, okay? Most likely you'll get something in between. So maybe you get the number 1, and you say, okay, well, I don't know exactly how much it is to the right, but I do know it's going to be more than 10%, but less than 20%. Okay, so I've got 9 degrees of freedom, and my test statistic is 2.34. How much do I have in the tail?
Between 0.01 and 0.02.
So 2.34
Oops. Then point
with 9 degrees of freedom.
0.02 and 0.025.
Yeah, so I don't know exactly how much, but I do know that the amount in my tail is going to be between 0.02 and 0.025. Is that right? No. No. 2. My eyes are playing tricks on me.
Yeah.
Yeah, 0.025. Okay, so we don't know exactly how much, but we do know that the amount in my tail is between 2 and 2.5%. Okay, and this is where things might just feel a tiny bit awkward, okay, especially the first time you see it. Okay, what we observed was a difference of 96.6 between these two groups, okay? So equally interesting would have been a difference of negative 96.6. Okay, so we're asking, what's the probability of getting anything, probability of getting a difference of 96.6 or more, and the probability of getting a difference of negative 96.6 or something more negative. Okay, and so therefore, if I drew this same thing and I put negative 2.34, the amount in this tail would also be between 0.02 and 0.025. So my total area in the tails, I don't know exactly what it is, but I do know it's going to be less than 5%, but more than 4%. Yes?
Could you repeat how you got 0.02 and 0.025?
0.02 and 0.025? Okay, so when you look in your t-table, go to the row 9 degrees of freedom, okay, and we're looking for 2.34, okay? Now we don't see exactly 2.34. What we see are, we see 2.262, I think, and 2.398. Okay, and so 2.34 fits in between these two numbers, and this corresponds to a tail area of 0.02, and this corresponds to a tail area of 0.02. Okay, so because the t is in between these two numbers, I know my tail area is in between these two numbers. Okay, so my total tail area is between 4 and 5%.
Why are we caring about the other side?
Just because, well, in the statement, I'm saying we're just interested if there's a difference between the two groups. Okay, so what I happened to observe was a large positive difference. But if I'm interested in a large positive difference, okay, unless I've got some preconceived idea of how this should work, I would also be equally interested. I would also be interested in equally large negative difference. Okay. So next week we'll talk about when we might only use one side or something like that. Okay. So at this point, the probability of observing my data or something more extreme if we assume the null hypothesis were true. So if we assume that the populations had equal means, the probability that I take two samples and just by chance get a difference of, what did I get, 96.6, the probability of that happening just by random chance is somewhere between 4 and 5%. So, what do you guys think? Is that enough for me to say I can rule out the possibility, or I mean, I'm going to take a chance and rule out the possibility that it happened by chance, or I'm going to say it's not enough evidence for me to rule out the possibility that it happened by chance.
So is
What's
that,
the percentage?
It's-
Well, no. What's the percentage in general that we say that?
Yeah, that's a good question. Okay.
95?
No. So the most common number we use is 5%. Okay, it's an arbitrary number that we've picked, and that has kind of stuck around as the number that we use. Okay, but for some reason we've kind of we've chosen this arbitrary line of 5%, and we say if things are smaller than 5%, we're gonna kind of just say, you know what, it probably didn't happen by chance, and something else is going on. If it's larger than 5%, we're going to say, we can't eliminate the possibility that it happened by chance, okay? That's an arbitrary line, and different researchers, depending on your situation, you might want to pick a larger number than 5% or a smaller number than 5%. It doesn't really matter, okay? That seems to be the number that has stuck, and most times if you want to get something published in a research article, you need to have a number of 5% or less. Some places will accept larger numbers, and it's it's kind of unfortunate that we've just drawn this line somewhere at 5% without. There's not a whole lot of reason behind it. You can trace the history of how this 5% came about, but I don't know. Why do we pick 18 to be the year that distinguishes between an adult and minor? It's arbitrary, but it's stuck, and that's become the norm. And so 5%, that has, it's a little arbitrary, but it's stuck, and that's become the norm. And so that's what we do. So at this point, because our total tail area is less than 5%, we're going to say, okay, we have enough evidence to say that the means are different. Okay. So this tail area, or the p-value, is less than 5%. So we say we have evidence supporting evidence to show that the means are different. Okay, so I will leave you with that. We'll see you guys next week. There's no homework due, but don't abandon your statistics knowledge. So.